This example comes out of section 10.2, products and quotients of functions. So this example is somewhat similar to the last, except we're given two functions this time as equations. F of x equals x squared minus 1 and g of x equals the square root of 3x minus 2. Hopefully both graphs or equations of graphs that we'd be able to sketch freehand without a graphing calculator. Now we're asked to determine h of x equals f times g of x, and then to find the domain and range of that. I personally always find the domain and range easier once I have a picture, but let's determine the function itself. H of x just equals this first function times this second function. You'll notice I'm careful with brackets, especially when you're dealing with the graphing calculator. You got to make sure you have these things in brackets. Not a lot will come out of me trying to expand multiplying x squared times that radical and then minus 1 times that radical. It won't look any better, so I'll leave it just in that form exactly as it is. Now if I look at some graphs, y equals x squared minus 1 is just a parabola, faces up, it's been moved down 1 unit. So if I look at its domain is x, where x is an element of all real numbers. It's just a plain old parabola, has no special features to it. Its range is that y has to be greater or equal to negative 1. So we have a parabola looking something like that. The square root function, hopefully we completed chapter 2 a long time ago. So the first one was f of x. Now if I look to do the same for g of x, you can obviously put it into your graphing calculator and see roughly what it looks like, and it's something like this. If you had g of x equals the square root of 3x minus 2, you may be tempted to write that as the square root of 3 times x minus 2/3. So you could describe by transformations a regular square root function being then horizontally stretched by a factor of a third and moved to the right 2/3 of a unit. So this coordinate here is 2/3, comma 0, where it touches the x-axis. This graph up here has x-intercepts at 1 and negative 1, which we'll talk about in a second. The domain of this graph is more interesting in that x does have to be greater or equal to 2/3. All real numbers otherwise are fine. And the range is that y needs to be greater or equal to 0, as is true with many of our square root functions we've looked at. So now if I looked to graph this combined function, this product function, it's not something I expect you to know off the top of your head. If you're looking at h of x equals x squared minus 1 times the square root of 3x minus 2, my first step personally would be to graph that on a calculator. So let's take a second to do that. You may or may not be somewhat surprised what this graph looks like, but it's a little curve, and if you zoom in closely enough, you can see a little bit what's going on here. It's undefined anywhere to the left of x equals 2/3. So its domain isn't too hard to come up with. It's just x, where x needs to be greater or equal to 2/3, just as the domain up above was. And it's the more limited of the two domains. The one up above just said all real numbers, but you can't square root a negative, so we're limited here. Now the range is a little trickier because this graph does do something kind of unexpected. It starts at 2/3, comma 0. It does have an x-intercept there, but it goes down briefly and then back up through 1, 0, and then off towards infinity. So it does have two of the x-intercepts of the graphs up above. The one to the farthest left, is undefined. I can't have a point at negative 1 since that can't be square rooted when I put it in that function. But if I'm looking for this actual, the range of this, I need to find the minimum. And to do so on your calculator, you're going to have to zoom pretty closely in at that part of the graph, because it's not immediately obvious where that minimum is going to be. But if you do make your window settings relatively small, you can use second trace minimum, and you end up doing the right bound, left bound kind of thing, and you can find out what this minimum actually is. So take a second to do that. Right bound, left bound, yes, and you get an unexpected, again, y value, that y needs to be greater or equal to negative 0.229 approximately as the range of this thing. So not something I would expect you to come up with on your own off the top of your head, but definitely something you can find using the tools at your disposal.